So now we'll take a look at the fragmentation patterns for ketones and aldehydes, and this will be the most complicated one we see. So the first is going to be alpha cleavage, and we've seen examples of that already. It's very similar. But the second is not going to be similar. This is going to be the McLafferty rearrangement, and it's a little bit of a pain in the butt. We'll spend just a little bit of time on that one, but let's look at that alpha cleavage first. So again, we're going to hit the ketone with a beam of electrons, and the most likely electron we'll knock out is one of those non-bonding high-energy electrons on oxygen. And in this case, there's our alpha carbon, the one bonded to oxygen, and we're going to break adjacent to him. And in this case, there's actually two alpha cleavage breaks that could happen. We're just going to look at the one on the right here. So in this case, the way this works, and let's just change colors for clarity, we're going to form half of a triple bond here using the radical electron, and then we're going to break this bond here, forming the other half of a triple bond, and then forming a radical back on this carbon. So and if we kind of look at what that looks like, we're going to have and now a triple bond to oxygen. So, and then we're also going to have a 3-carbon radical from this part of the fragment right down here. And if you notice, one of the reasons this is so stable is this is a resonance stabilized cation here. We can kick those electrons there, and we'll find out that the positive charge here is shared not just by the oxygen, but also by this carbon right here. And again, explaining why we do alpha cleavage to begin with, we form a resonance stabilized, fairly stable fragment, at least relative to some of the others we could form. And now on to the McLafferty rearrangement, and this one's a little bit of a pain in the butt. So the way it works, we often letter with Greek letters the carbons related to a ketone, and we've got the carbonyl carbon, and that doesn't really get a letter, but adjacent to it, you give the letter alpha, and then beta, and then we'd go to gamma, delta, epsilon, so on and so forth. Usually don't need to go that far. But the idea that McLafferty rearrangement is only possible if on either side of a ketone or on the only side of an aldehyde, you have at least up to 3 carbons. So at least a gamma carbon. You require gamma carbon. And we're going to form a new bond between the oxygen and the gamma hydrogen to kick this process off. So this unpaired electron here, the radical on the oxygen, is going to form half the bond between it and hydrogen. The other half is going to come from the gamma carbon hydrogen bond itself. So we have one electron remaining in this bond, and that's going to be used to form a pi bond between beta and gamma. The other half of that pi bond comes from the bond breaking between alpha and beta. And the other half of that bond, the one electron left, just forms a radical on alpha here. So a little bit of a complex process, but essentially we're breaking the bond between alpha and beta here, and then forming a double bond between beta and gamma. So if we look at the product, I'm just going to start with beta and gamma real quick. So in this case, there's beta, there's gamma, and now there's a double bond between them. If gamma had been bonded to any additional carbons, we would have represented that as well. So we're also here going to have so the oxygen now bonded to a hydrogen, still having a positive formal charge. So, and then we'll have this alpha carbon over here having the non-bonding radical electron here. And in this case, this thing is resonance stabilized. Still having a positive formal charge on the oxygen, but again, forming a resonance stabilized cation here. This again is a fairly stable fragmentation pattern. Note that this is unusual. Usually we get a cation and a radical, but this one's still both the radical and the cation. This is your result of the McLafferty rearrangement.